So, in this slide we are going to study the relationship between Nash equilibria and evolutionary stable strategy. We have already noticed that when we talk about evolutionary stable strategy, the game has to be symmetric. So, I have taken a symmetric game, 2 by 2 game. So, player 1 has these two strategies S and T, and player 2 also has these two strategies. So, it is symmetric. The payoff, because if both are playing S, then their payoff have to be equal, and when they both are playing D, their payoff have to be equal. And when one is playing S, other one is playing T, their payoff would be different, but the situation would be reversed when we move from this box to this box. So, this is what is described as a Nash, the symmetric game. Now, for the symmetric game, we have to obtain the condition for which SS is a Nash equilibrium, because when we talk about evolutionary stable strategy, we will compare it with S comma S being a NE, and if this is the same setting, is this S evolutionary stable? That is the comparison we are going to have. So, when do we get S comma S as a Nash equilibrium? To get S comma S as a Nash equilibrium, S is the best response of S for both the players. So, it means when S is the best response, when player 2 is playing S, player 1 has these two options S and T. When S is the best response, when A is greater than or equal to C, otherwise S cannot be the best response. Let me write it, this is what I have written here. S is a best response, so A has to be greater than or equal to C. And condition for which S is evolutionary stable, there we have to say that this S gets invaded by T. So, invasion is by T. So, this is x, this is 1 minus x. How much does S gives? S gives A 1 minus x proportion of time plus B x proportion of time. And how much is T? T is C 1 minus x proportion of time and D x proportion of time. And for S to be evolutionary stable, this value has to be greater than this value. So, A 1 minus x plus B x has to be greater than C 1 minus x plus dx. What is the requirement? Remember, x has to be very, very small. We do not allow for large invasion, because we say it is a biological process, mutation happens at smaller level. So, if x is very, very small and A is greater than C, then we are done with it. If x is very, very small, the effect of Bx and dx are going to be negligible. So, if A is greater than C, then there definitely exists one x for which this side is greater than the other side. So, the one requirement is A is greater than C. For evolutionary stable strategy, that S is evolutionary stable strategy, one requirement is that A is greater than C. The other possibility is that what if A is equal to C? If A is equal to C, then B must be greater than D, then only left hand side is going to be larger than right hand side. So, S is evolutionary stable. What it means that either A is greater than C or A is equal to C and B is greater than D. And S comma S is Nash equilibrium. What is the requirement? A is greater than or equal to C. Now, we have to compare this with this. So, we can say that if S, let me write it here, S is evolutionary stable strategy, it definitely implies, because if S is evolutionary stable strategy, either A is greater than C or A is equal to C, both imply that A has to be greater than or equal to C, and therefore S comma S is a Nash equilibrium. How about the other way? If A is greater than or if S comma S is a Nash equilibrium, can we say that S is evolutionary stable? We cannot necessarily say that S is evolutionary stable. Can you think of A is greater than or equal to C? It is very much possible that A is equal to C. We can think of here 5 comma 5 and here is 5 comma 3. But in that case, because Nash equilibrium does not impose any restriction on B and D, so we can have 3 comma 5 and we can have here D larger 4 comma 4. So, of course, in this case S is not going to be evolutionary stable, but nevertheless S comma S is a Nash equilibrium. Here B is less than D. So, there is no bearing of B and D value on S comma S being a Nash equilibrium, but it has a bearing on S being evolutionary stable strategy, particularly when A is equal to C. So, we can say that if a strategy S is evolutionary stable, then S comma S is a Nash equilibrium, but unfortunately the converse is not true. Let me give you one example, that sex ratio as evolutionary stable strategy. Again, I am not getting into the full mathematics, but just to tell you that most of the animals you look at, including humans, male and female ratios are closer to 1 comma 1. So, how can we justify it? There is evolutionary stable logic there. Suppose female births are less common than male. So, a newborn female then has better mating prospect than a newborn male, and therefore can expect to have more offspring. Therefore, parents genetically disposed to produce female tend to have more than average number of grandchildren born to them. Therefore, the genes for female producing tendency spreads and female birth becomes more commoner. As the 1:1 sex ratio is approached, the advantage associated with producing female dies away. The same reasons hold if males are substituted for female throughout, and therefore we get 1:1 as equilibrium ratio. So, just to round this up, let us take one more example, that in population there are two kind of, whether it is a human population or any animal, we take we see two kinds of animal, one which are gentle and second which are aggressive. So, hawk and dove game explain why aggression is present within population, but it is not always seen. So, we can say symmetric hawk and dove game we can talk about. We can take two indistinguishable individual. They both must decide whether to share a resource or demand the resource for themselves. If only one individual demand the resource, play hawk, then C obtains the whole resource, let us say the value is V. If both demand the resource, they fight, each win with probability 0.5, thus obtaining the resource. The loser pay a cost of C due to injury incurred, and it is assumed the cost of injury is more than worth the resource. C is greater than V. So, this is the payoff we have written. The story was different earlier when we talked about game of chicken, but exactly this is what we get. So, let us say that the population hawk types are p fraction and dove types are 1 minus p fraction. You can say that population is made of dove and it is being attacked by hawk. What happens for hawk type? P proportion of the time hawk will meet a hawk. So, the payoff is going to be p multiplied by v minus c by 2. Remember, we have already assumed that c is greater than v, and p proportion of 1 minus p proportion of time it meets dove. So, 1 minus p multiplied by v, and this is the payoff. And for dove type, p proportion of time 0, but 1 minus p proportion of time v by 2. So, this is the payoff. For example, we can take v is equal to c and c is equal to 10. What will happen? For Hawk type, the payoff comes out to be 6 minus 8p, and for Dove top it comes out to be 1 minus p by 3. We can draw it. How does it look like? Where p is a number between 0 to 1, but p is supposed to be closer to 0. So, let us say here is 1, here is 0. Now, we can do for the Hawk type 6 minus 8p. So, when p is equal to 0, it starts at 6 and it goes to minus 2. We can say it is like this, 6, and here is minus 2. How about for Dove type? When p is equal to 0, it comes out to be 3, and when p is equal to 1, it is 0. So, it comes out to be something, it starts at 3 . So, what will happen here? Let us say we begin, this is Hawk and Dove population. This is for Dove and red one is for Hawk. So, if at very low level of p some Hawks are introduced in Dove's population, let us say here, what is the case at low level of p? Hawk has higher fitness. So, fitness will increase their population. Their population will increase, proportion will increase, because Hawk are fitter than Dove and they will move in this direction. Similarly, I want you to calculate what would happen if among Hawk population Doves are introduced. We can check here, in Hawk population if Dove are introduced. We have already taken v is equal to 10 and c is equal to 6. So, we can write here v minus c by 2, this is the minus 2, 10, 0, 0, 10 and 5, 5. This is what we have. You can also check what happens here. What we have done, that in population of Dove, Hawk has been introduced. We will do it opposite way. Now, let us say that population is made of Hawk altogether. So, let us say that this is 1 minus p and Dove is p. How much is the fitness of Hawk? It is minus 2 multiplied by 1 minus p plus 10 multiplied by p. So, minus 2 plus 2p plus 10p, 12p minus 2, and Dove are going to be 5p. How would it look like in this particular case? Again, when p is equal to 0, it is minus 2 and minus 2 to 5 it will. So, roughly the inverse of this image you get. So, what is going to happen? As at this level, if you are introducing, population is fully made of Hawk and you are introducing Dove, then Dove will keep on increasing, and this is where you will have stability. You will get neither fully dominated by Hawk nor by Dove, you will have a mixed population, and therefore, in society we find both kind of people, some of them are aggressive, some of them are gentle. So, this is the rough bit on evolutionary game theory. We will have some problem sets. We will also try using the problem set, we will try to see the application of evolutionary game theory in business world. All the best. Thank you.